go ahead and get started. So welcome back everybody to EE240. So last time we were just basically finishing up with constant, or rather I should say biasing and references, which usually involves some sort of constant x, where we talked about, basically you get to figure out what x should actually be. Before we sort of just wrap up with that, there's sort of one last quick thing that I want to talk about there, and then we'll move on to really the main topic for today, which is high-speed links and kind of an overview of that, which is going to be important for obviously the project, which has been handed out. Any kind of questions or anything like that on the material so far, or the project, which was indeed posted earlier this week? You guys can all build all kinds of references now, and it's all constant versus all possible other inputs, and etc., right? Okay, so just to, maybe we'll dive back in and that'll get some discussion going. So the last sort of constant x reference thing that I wanted to just quickly talk about was this so-called constant GM reference. So we talked about how you could do, for example, a band gap that would give you a constant voltage. We talked about some other references that would either give you some sort of proportional to temperature, either voltage or current, or, for example, we talked about how to sort of generate current sources that were independent of the supply. But in many cases, that's not necessarily what you care about. Sometimes what you care about more is, for example, just how you get like a constant GM, for example. Because as an example, if you can get a constant GM, then GM is usually the thing that's sort of setting a lot of the performance characteristics we care about. And so that's one of the sort of most common and, let's say, interesting references that people are interested in. So let's see how we might be able to do something like that. So as you can imagine, it's going to be very similar to sort of a lot of these so-called, let's say, recursive things that we have looked at before, where we're going to use essentially two sets of current mirrors to basically make sure that the current on the two sides is equal, and to sort of create this so-called self-referenced type of thing, meaning self-biased, I guess I should say. Because remember, self-biasing was one of the key tricks that we had to use in order to make things not depend on the power supply. But so the final sort of trick we're going to play here is actually something that looks quite innocent, but is really what's going to be sort of what's allowing us to get a so-called constant GM. Okay? So I've just sort of drawn this self-mirrored circuit here, but actually I'm going to use this in a slightly different way than we have previously. So these two devices, I'm going to size them to be the same as each other. So this is really going to be a one-to-one current mirror. So that's really to try and get the currents on the two sides to be equal. But unlike in some of the previous circuits we looked at, I'm going to try and make this device right here quite big. Okay? And we're going to see why I did that in 1 second here. Okay, so if I made that device very big, remember kind of if I want a constant GM, that's kind of saying something like I somehow want a V star to show up across, in this case, a resistor, right? Because if I get a V star to show up across a resistor, and then the current is set by V star over that resistance, that means that the GM should therefore be fixed. Okay? So what I'm basically saying here is that I somehow want V star to show up right there. Okay? Well, at least for a long channel device, roughly speaking, V star is kind of like related to VGS minus VTH. Right? Now remember, I'll emphasize this again. V star is really not that. It's really not set by this. It's only if you think about sort of a long channel device, then the relationship is exact, and everything else is sort of by analogy. But we'll see in a second that if we do things this way, basically it'll give us the behavior that we want. Okay? So let's assume that V star is indeed related to VGS minus VTH. So now, can anybody tell me, maybe if you've seen this before, or you have an idea already, why is it that I made this device right here big? And by big, I mean like really big. What's that going to sort of do? Or rather, how does that make it so that V star is somehow going to magically show up on that resistor right there? Any thoughts?
If it's big, the overdrive is pretty small.
Okay.
So the VGS will be the VGS of the mirrored version.
Okay, well, so let's maybe cut that into a couple of pieces. So this right here, by definition, has to be VGS, right? Because that's just, again, I didn't do anything. I'm just sort of relabeling things, right? So if that's VGS, then again, of course, that voltage right there also has to somehow be VGS. But if I make this transistor really big, then basically the amount of extra voltage it needs beyond VTH should be very small, right? In other words, and let me maybe do it in a different color just so it's clear. In other words, by making that transistor big, I'm trying to make it so that that voltage drop right there is just VTH, right? So if that voltage drop in blue is just VTH, then to the extent that this right here is roughly true, then I should indeed just get V star across that resistor there, right? So just to see how that gives me a constant GM, just remember that, of course, the bias current is just going to be VGS minus VTH divided by RB, right? Which is, again, just kind of, by definition, I'm just walking through that loop right there. Okay? And then, of course, IB should be set by, to the extent that VGS minus VT is roughly V star, then IB is now V star over RB. And so if you remember that GM is equal to 2IB over V star, then if we just rearrange things, then of course that's going to say that GM is equal to 2 over RB. Okay? Which is kind of, as we said in the get-go, what we wanted here was a constant GM reference, right? And notice it doesn't depend on the supply, doesn't depend on hopefully much of anything except for just what is the value of that RB, right? So now if you can make a good, nice, precise RB somehow, then your GM will be controlled by that RB. Okay? Does this kind of make sense to everybody? Or? By the way, just to be clear, hopefully again maybe somebody has seen this before, if you wanted to basically use this to actually create another circuit that has this known GM, how would you do that? Like what, how would you, let's say, mirror something off to get a transistor that has that same GM? Any thoughts? It's not a trick question, by the way, so let's maybe give you a couple of hints here. So let's say they have a VBP right there, we have a VBN. Could you do anything with those voltages?
Tie them to the gate of some transistor with same width.
Yeah, exactly. Right? So if I just take that VBN and tie it to the gate of some transistor with the same width, then guess what? I'll get that GM, right, out of this transistor. Okay? So that's exactly how you use it. In fact, actually, a lot of these references, that's basically how you use them. You just mirror off one of those voltages there to get a transistor that you know will have the same current. Okay? Any questions on this before we go ahead and move forward? Or so again, you guys can all build any, if I say I want a constant x where x is arbitrary, you'll know how to build that reference, right? All right, well, since nobody's saying no, I'm going to take that as a yes, so I'll hold you to it on the exams. Okay, so with that, let's actually go ahead and move forward. So the main topic we're really going to be talking about today, and actually kind of over the next few lectures, is actually talking about essentially high-speed electrical links. Okay, and I'll sort of quantify what I mean, or maybe specify what I mean more by that in 1 second. But again, just as sort of a reminder as to why we're changing gears a little bit here, is one of the main goals of the project is really to get you guys exposed to the fact that no analog circuit sort of exists in isolation. There's always a larger system that you're going to be talking about. And so although people usually like to sort of just come up with a bunch of specs and assign them to each and every single block that you might be building, oftentimes that's really not the right way to approach the problem. Okay, because as an example, you'll see if you've taken a look at the project already, you saw that this project had to do with sort of building a front-end amplifier. Well, even if you build the best front-end amplifier in the world, if that thing is, like some small fraction of the overall budget, and somehow by just tweaking some other component somewhere, the overall system would have been much better, then you're much better off actually focusing on that other component. Or maybe tweaking this amplifier, maybe make it a little bit better, or a little bit worse, to help you with the rest of the system. Okay? So again, this is really sort of the whole reason we're talking about this is, okay, A, I know something about links, but really B, it's actually to give us an opportunity to look at a larger system and how we would make trade-offs between different pieces of that system. Okay? So first of all, just to sort of make sure it's clear to everybody, when I say high-speed links, what I really mean is essentially high-speed communication from one chip to another chip, usually sort of on the same board, although sometimes over a cable. Okay? And when I say high speed, I really mean high speed. So I'm talking like 5 to 10 gigabits per second, okay, per each, let's say, pair of wires. Okay, so just to kind of give you a little bit of motivation as to why something like this might be interesting and where people sort of worry about these things, what I've done is I've actually taken just a picture of a PCB that I'm guessing actually many of you, although maybe you don't know it, are actually quite familiar with this particular PCB here. So, I don't know, maybe somebody has really sharp eyes or something. Anybody know what this PCB happens to be? Anybody tell, or maybe just have a guess?
Gaming console.
Say that again?
A gaming console.
Ah, it's a gaming console. Which gaming console?
PlayStation.
Yeah, it's the PlayStation 3, actually. Okay?
That's the console word on the lower left corner.
Ah, well, that's actually the name of the website where I stole this from, so that just happened to be a lucky guess. But if you pay close attention, you can see there's like a Sony computer entertainment inside of here somewhere, labeled on the chip. So that's usually a better guess. It's a little bit washed out, but you know, if you look at it closely, trust me, it's there. Okay? So this happens to be the PlayStation 3. Okay? So this thing right here is kind of like the main processor. It's called the cell. It's got 9 cores on there, runs at, I don't even remember, 5 gigahertz or something like this. But bottom line, it's doing a lot of stuff. And when it does a lot of stuff, it needs to talk to the rest of the world really, really fast. Okay? So this is the cell right here. This is actually the graphics engine. You can kind of see this is some memory that's talking to the cell. There's actually some more memories distributed around here talking to the graphics processor. This is some, I think, legacy piece thing right there. But basically, if you see these, like, you can kind of see there's all these wires running back and forth between, for example, the cell and the graphics processor. That's sort of the wires actually carrying all this high-speed data back and forth. Okay? So actually, just to give you sort of a rough idea, all of those wires right there, and there's quite a few of them, that's transferring about 30 gigabytes per second of data back and forth. Okay? And I did not get any of the units wrong there. So I really do mean your entire iPhone in 1 second. Okay? So really fast. Lots and lots of data flying back and forth. Right? Okay? So what's kind of one of the most important things you think you might care about, other than just obviously how fast this thing is running? What else do you think you might care about from a kind of design standpoint? So we've been talking a lot about over and over and over again in this class.
Noise.
Okay, certainly you're going to care about noise. We're going to talk about more about that in a second. But noise is kind of like for us nerdy folks who actually have to build this, right? Somebody else who's maybe like putting this console together or actually using it and has it plugged into the wall. What might you care about? Power, right? How much you got to pay in the electric bill? Okay. So turns out that particular interface that I circled right there takes about 7 watts of power. Okay. Now, that may not sound like all that much, especially given how fast we're going. But I claim actually, you know, if I wanted to, let's say, take this up by another factor of 10, let's say I wanted 300 gigabytes per second, which, by the way, today is, you know, people are building things that look like that. You probably don't want to be paying 70 watts for it, right? Expensive. That's like your entire, you know, that's a light bulb that you've plugged in and is running all the freaking time, right? So basically, much like in a lot of the things we've seen before, a lot of what we're going to be talking about sort of in the context of the project is basically how we're going to use some of the class material to actually figure out how would you build these things that are running at these really, really high speeds, but without burning too much power, okay? Now, by the way, in case you think, you know, all these issues and sort of all the stuff that we're going to be talking about is limited just to like these 2 chips, you can actually see there's these traces all over the place. all of those are some form of high-speed link. In fact, if you even look over here, this is like the Ethernet controller that goes out into like, that Ethernet plug right there. All these, high-speed lines there, all of that is really directly related to the stuff we're going to be talking about here. Okay, so these links are kind of all over the place. They're pretty hard to actually build right. There's lots of sort of interesting challenges there. And also it's going to give us an opportunity to, again, sort of look at a bunch of different components. So that's why I'm going to be spending some time on it here in the class, and it's also actually going to motivate a lot of the rest of the material that we're going to be talking about. Okay? So, in terms of links, there's really sort of two very basic issues that potentially one could be thinking about. And obviously this is at a very high level, but the two basic issues are actually quite simple. And they both essentially have to do with how do you get digital data from point A to point B. So the first one is essentially what's called signaling. What that means is just sort of physically, what are you doing to actually transmit data from one side over to the other? Okay, from, for example, one chip over to the other. Okay, so this has to do with like, are you sending a voltage signal? Are you sending a current signal? How do those signals get messed up as they go from one point to the other? And things of that nature. So most of the stuff we're going to talk about in the class is going to be related to signaling. But it turns out there's another sort of very important thing that you would worry about if you were actually going to build a link. And that's really timing. Okay? Now, timing is important because basically what I mean by that is, how do you decide which bit is which? Because obviously over here at the receiver, essentially all you're getting is some voltage or current or whatever waveform, right? So even though once I've gotten that waveform, I need to decide what's like the time boundaries between the bits that I'm going to receive, right? So as an example, as I kind of drew it here, if I was sampling everything at kind of the ideal spot, I would kind of make decisions about what's a 1 and what's a 0 at each one of the points that I kind of marked right there. But imagine that for some reason, I didn't do a good job or something's not working quite right. Imagine I instead was trying to make decisions like right where all the blue arrows are, right? That's probably bad news, right? Because I can't really tell exactly was I receiving a 1 at this time or was I receiving a 0. I'm just kind of getting some garbage value, right? So again, for most of this class, we're going to actually focus on this side of things, the signaling side. And we're going to assume that somehow magically somebody gave us the timing. In other words, that we're always sampling the bits at exactly the right spot. But maybe towards the end, we'll talk a little bit about sort of some of these issues and some of the circuits that you might use to actually solve these problems as well. Okay? So, the first thing we need to just sort of remind ourselves of is what's really different about signaling in this high-speed link context, where again, what I'm talking about is sending signals from one chip to another. Because after all, right, when we even talked about our analog stuff, we talked a lot about, okay, there's just wires and things like that, and you may have some amplifier driving another amplifier, and so maybe I'll just draw that. So we said, okay, fine, those wires aren't really perfect. So maybe we would have said, okay, if that wire's long enough, it's got some capacitance associated with it. And of course, if it's really long enough, it probably has some resistance associated with it. But so the real question is, why is it that when we talk about chip-to-chip links, we have to do something, much different or more sophisticated than just what we've had thought about for our on-chip wires? Well, of course, the answer is that, unfortunately, the model we usually draw for our on-chip wires is just not physically correct once we get to the off-chip wires, okay? And the reason for that is pretty simple, right? When we're talking about stuff on-chip, the dimensions of those wires are generally pretty small in comparison to the wavelengths of the frequencies we're interested in, right? Whereas when we talk about things, on, let's say, a PCB, even if this is only like a few inches, right, relative to like the multiple gigahertz of basically frequency we're talking about, this is actually a pretty substantial fraction of the wavelength, okay? What that basically means is you can't just sort of use the same model anymore. You can't just think of the wires as at worst being something like a resistor and a capacitor. Okay, we actually have to think of them as something slightly more sophisticated. Well, so turns out the thing that we need to think of them as is what's called a transmission line. So how many of you guys have heard of transmission lines before? Okay, great, just about everybody. So really just as a reminder then, a transmission line is basically just a model of the wire when you can't ignore the speed of light. Okay? So it's usually drawn as this kind of like thick, I don't know, circular thing. That's usually sort of how people indicate a transmission line. Okay? So what's happening in a transmission line is, because the speed of light is finite, it basically tells you you can't put some signal over here and expect that it's going to show up at the other side instantaneously. Right? It's always going to take some time for this signal to propagate from this point over to that point. Okay? In other words, there's always a delay associated with that line, which you can imagine is kind of related to like the length of that line. Okay? Now, from a sort of, if we wanted to just draw a simple model that, like, you know, we as let's say circuit designers rather than electromagneticists like, you know, make it easy for us to think about things. If you kind of think about something that has a delay, that means somehow we have to be sort of inserting elements that are creating that delay, but are not sort of like creating some frequency dependence somehow. And by the way, in order to get delay, that kind of means that somehow you have to be storing energy somewhere, right? Well, if you kind of think about it, what that basically means is that we're going to end up with something that sort of looks like this. Okay, so we can kind of say, okay, well, each one of those little pieces of wire, it's got some current flowing through it, so it has some magnetic field, so we can kind of model that little piece of it as being an inductance. But of course, there's also a voltage there, so there's some electric field lines down to, for example, ground. So there's also a little capacitor, right? So essentially, we can sort of model our transmission line as this distributed LC network like this, okay? So clearly, we're going to store energy in this. You can actually kind of quickly figure out that there's going to be delay in this thing because, you know, you put some, let's say, voltage step right there. Well, the inductor has to charge up, then it'll charge up the capacitor, then this one has to charge, and so on and so forth, right? But I also said that I just sort of want somehow I want that energy to kind of get from point A to point B. And I want to sort of figure out what is the, let's say, frequency dependence of that. Or, you know, if I do, let's say, a sinusoid over here, if it's really just a wire, then this wire shouldn't be like changing that sinusoid any, right? Well, so the good news is, and this is one of those sort of classic EE240 kinds of things, if you look at this thing, since I haven't put any resistors inside of this model, which obviously isn't exactly correct, but we'll come back and fix that in a second, there's no way for energy to actually get lost, right? It all has to be stored inside of this wire somehow and eventually show up at the output, okay? What that kind of means is that, as an example in particular, if I put like a load over here, what that basically means is that I have to be presenting some sort of real impedance, right? I must be just somehow grabbing the energy from over here and eventually dumping it into that resistor right there. So if I was to keep on breaking this wire up into smaller and smaller pieces, I just keep drawing sort of like this little L and C networks like this, right? So eventually I can almost even say that this thing just looks like an infinitely long or infinite number of sections, where each section has this little L and little C. So does anybody remember what is the Z, or the input impedance, looking into there for something that has all these small little sections like that of L's and C's?
Square root of L over C.
Yeah, exactly. It happens to be square root of L over C. Okay, and it's, again, one of those classic like EE240 kind of problems where they give you an infinitely long network of repeated things and ask you what's the impedance. Okay, same exact thing. So that impedance is going to be square root of L over C. Okay? So if you look at like typical transmission lines, even on our PCBs, that Z0 is typically somewhere between 50 to 100 ohms. Okay? Maybe even a little bit lower than that. Maybe like, I don't know, 30-ish ohms on the low end. Okay? But not too huge of a range. And actually a fairly low impedance. Okay, so that's kind of the zero order thing about transmission lines is just they have delay and they have a characteristic impedance. But actually they can also create some more fun for us. So actually to see what might be more interesting, let's go back and take a look at this board right here. Right? So if you look at these sort of lines that are on the PCB, these are probably the transmission lines, but to get from the chip into that line, I probably have to go through the package, right? You can imagine that package probably has some pretty different characteristics than these things on the board over there do. So in other words, what's eventually going to happen is you're going to have to take one transmission line, and actually I guess I'll draw it down here. What eventually is probably going to happen is you're going to have one transmission line with, let's say, a certain characteristic impedance. Eventually, it's probably going to have to talk to another transmission line, where that other transmission line may have a slightly different characteristic impedance. Okay? Because you can imagine, like, changing the widths or the spacings of the wires, that's what's going to change those impedances, or the characteristic impedances. Okay? In other words, anytime you have like a physical junction of two different things, then it's kind of like saying we have two different transmission lines that are talking to each other. So now what's a little bit fun is that because everything is sort of distributed, we can actually get some very interesting behaviors out of these things. Okay? And we need to sort of understand what really is going to happen if I, for example, launched a voltage wave right there and I hit this junction. Okay? So in order to do that, and again, this is hopefully review, but remember, essentially, what's going down that transmission line is like an electromagnetic wave. Okay? So anytime that wave sees a discontinuity, basically two things can happen. One is that some piece of the wave will get transmitted forward into the next transmission line, and some piece of it will get reflected back. Okay? So now to sort of understand, or to give us some way of coming up with some equations as to how this is going to impact us, what we basically need to do is sort of figure out, okay, how much of the thing is going to get transmitted and how much is going to get reflected. It turns out to do that, we really just need to keep track of two things. Okay? So let me just label this V reflected. Let me call this V transmitted. Okay? So we really just need to know sort of two things. So the first is that if I look at any one point, then of course KVL has to hold at that point. In other words, the voltages on a loop have to be equal, right? Similarly, also just sort of very basic like physical thing, power always has to be conserved. Okay? So let's say how we can use that to actually figure out what will happen when we have one of these junctions like this. Okay? So first, if I just use the fact that the voltages have to be equal, then what I'm basically saying is that VI, which of course, when I launch it over here, is going to have to eventually show up right there. Then basically, VI plus V reflected, where again, V reflected is the voltage that's going to come back. That basically has to be equal to the transmitted voltage. Okay? And you can kind of think of this even at sort of like DC, right? Because, for example, if I waited long enough, then this V reflected will come back and show up at that VI. So this whole thing will just be like a wire. So it better be the case that this VI plus the V reflected is equal to the transmitted voltage that eventually shows up there, right? Because at DC, this whole thing should just be a wire. Okay? So that's my first sort of constraint. My second constraint is, again, that power has to be conserved. Okay? So, let me ask you guys, how much power is being delivered into that first transmission line due to the input voltage source? At the very beginning of time, before you even know what happens down over here. How much power are you delivering? What does this sort of transmission line look like?
Square over Z1.
Say that again?
V square over Z.
Yeah, the power is going to be VI squared over Z1. Because remember, initially, the transmission line just looks like a resistor. It's just grabbing the energy from the input source. Okay? So the power I'm launching into the system is just VI squared over Z1. Okay, so once I get to this junction, that power had better be conserved, right? Otherwise, something is wrong. It's like, power can't just magically flow out of the system, right? So that basically means that the power from the reflected wave plus the power from the transmitted wave had better be equal to this input power, right? Okay, so how much power does the reflected wave have? If I go from this junction and I go look backwards, and I put a voltage of V reflected back onto that transmission line, how much power does that take? Again, not a trick question.
You reflect the square over Z1?
Yeah, exactly. Right? Because I have a voltage of V reflected, and it's going to see an impedance of Z1 looking to the left there, right? Okay, so how about the transmitted wave? How much power does that have? Yeah, exactly. It's just V transmitted squared over Z2. Okay? So it turns out those are the only two things you need. If you use those two equations, because of course I only have two unknowns here, so if I tell you what the input voltage is, and I want to know what's the reflected voltage and what's the transmitted voltage, and I know what Z1 and Z2 are, I can just take those two and put them together, and what you'll get is that the transmitted voltage is just 2Z2 over Z1 plus Z2 times the input voltage. And the reflected wave is just equal to Z2 minus Z1 over Z1 plus Z2 times the input voltage. Okay? So by the way, again, how many of you guys have seen all this stuff before? Or at least seen these equations before? Okay, a few of you, good. So this is sometimes referred to as like the telegrapher's equation. Okay, it's not really too important in terms of where the name and all that. But if you just sort of look at it intuitively, it kind of makes sense in the following way. So notice if Z2 was really, really big, like infinite, then what you'd get is that the transmitted voltage is just equal to twice the input voltage. Okay? So here's another sort of interesting question here. Actually, did I get that wrong? Yeah, no, that's right. How is it that sort of happens? How am I getting like a gain of 2 there? Am I breaking some sort of causality or? Yeah, exactly. Right? So essentially what's happening here is that I'm reflecting 100% of the wave back. And so it looks like, essentially, that everything is showing up. Right? Or I should say, as Brian was saying, that you get constructive interference. Right? Now, just in case this sort of bothers you, don't worry about it, because all this is really saying is that if I had something that looked like a 50 ohm line, a 50 ohm source, driving this transmission line, and then showing up at an open circuit over here, well, remember, initially, that line just looks like a 50 ohm resistance, right? So what would show up right here would have been VI over 2. But actually, when it gets to that end point right there, it'll say, hey, wait a minute. Actually, I don't have anywhere to deliver that energy, right? So actually, that voltage would completely reflect back, come back to this point right here and say, okay, actually, sorry, you were supposed to be VI, right? Okay, so now, why do I bother mentioning all of this? Well, you can imagine, if this line here is kind of long, it's going to take some time for you to figure out that this was really the right voltage, right? Remember, what we're kind of trying to do is we're trying to send digital bits at a really high speed, right? So actually, if I'm trying to send these things at a really high speed, what I really want is I want exactly whatever I transmitted to show up nicely at the receiver, right? But if I've got this thing where I have to, like, initially I think I'm transmitting one thing, but then it comes back and I actually ended up transmitting something else, you can imagine I can get some very weird looking waveforms right there, right? That won't exactly be what I transmitted. So if I get some really weird looking waveforms over there, I may not actually receive what I intended to send, okay? So again, why do I kind of go through all this? Because it's actually pretty hard to completely avoid having these kinds of junctions here. But really, if you want to make sure you get a nice sort of clean waveform, you should try and make it as smooth and clean as you can, okay? And in particular, when you build your circuit, unlike, for example, in our on-chip wire example, where let's say we just have one amplifier driving another amplifier, and there's just like a capacitor sitting right there. When you have one high-speed transmitter driving a receiver over a transmission line, what you really want to do is actually terminate that line and as close to the characteristic impedance as you can, okay? Actually, not only on the receiver, but in fact, you even want to make the output impedance of the transmitter also as close to that characteristic impedance as you can, okay? Because basically, if you don't, then what will start happening is you'll transmit something, it'll reflect, it'll come back, it'll reflect again, and you get all these really interesting physics problems that, if you guys took some class on this, I'm sure you spent lots and lots of time analyzing what exactly was the time domain waveforms that happened to show up from this thing, okay? This is, just in case, you guys don't remember, this is like having these things with unterminated or, improperly terminated transmission lines is like, that's one of these so-called bounce diagram problems, where you have to keep track of what happened to the energy as it bounces off each one of these different junctions, okay? So bottom line, in all of the sort of high-speed links that we're going to be talking about, you should be using terminated systems. In other words, you should try and keep everything as close to the characteristic impedance of those lines as you can, just to make sure that you don't run into these kinds of problems, okay? Now, actually, it turns out that sending a signal from point A to point B is hard, not only because of the fact that we might have a bunch of different transmission lines with different impedances that might cause reflections, but actually, of course, real transmission lines have just physical loss associated with them. And there's kind of like two sort of mechanisms for that. So one is just, any wire, of course, has some resistance associated with it. So as you move a voltage along that resistance, there's going to be some heat that gets generated, right? In other words, you're going to lose some of your signal. Turns out at high frequencies, it's even worse than that, because at very high frequencies, the sort of wave can only propagate around the edges of the wire. Okay, this is called the skin effect. So at high frequencies, just all of the current's really flowing around the sort of periphery of the wire. So what will happen is that actually, even if at DC you have a pretty low resistance, once you get up to sort of higher frequency, the resistance will actually start going up, because the kind of cross-sectional area you have available starts going down. So that's called skin loss, and it's due to, of course, the skin effect. That loss is proportional to the square root of frequency. But just keep one thing in mind, that's in dB, okay? So in other words, if you go like to a twice as high frequency, or actually let's make it 4 times higher frequency, you'll get double the number of dB of loss. Okay, so that's kind of a funky thing to think about, but that's the way it works. Okay, so that's one mechanism. The other mechanism is actually so-called dielectric loss. This has to do with, even though we like to think of things like an oxide as just being a perfect capacitance, actually at high frequencies, the little molecules inside of it, or really the little electrons inside of that dielectric, they get shoved around or yanked around by the electromagnetic wave. And because they can't necessarily move with the wave at the same exact speed, you actually end up dissipating power in dragging those electrons around. Okay? So essentially that creates another effectively shunt current path. That loss mechanism is called dielectric loss. That one is proportional to frequency, but again in dB. Okay? So if you usually look at like the transmission or like kind of like the transfer function of one of these transmission lines versus frequency, you'll see you usually get very, very low loss at low frequencies. As you start going up to higher and higher frequency, first usually the conductor or the skin loss kind of comes into the picture. And then once you go to high enough frequency, you're basically dominated by that dielectric loss. Okay? Now, most of that has to do with sort of like materials and, let's say, physics issues. But again, if we sort of look at how good of a signal, how good of a job can we do in getting our signal from point A to point B, a lot of times it's not just about those material issues. It's also often just how we physically constructed our PCB. Okay? So as an example here, what I'm showing is a very common situation where you want to get a signal across the PCB, but you hit some blockage from some other line. And so you need to basically build a via to go around that line in a different metal layer. Okay? Well, remember everything is a transmission line, right? So if I was to kind of draw an equivalent model of this, I'm going to get something that looks like the following. So I have my nice transmission line maybe coming from there. But then when I hit that via, this thing has some height associated with it, right? So it's almost like I just have a little piece of transmission line that at the end, you can see there's nothing really connected at the bottom there. I kind of just have like a stub, right? So I just have maybe like some capacitance hanging off of there. And then I'll keep going off into the next transmission line. Well, so let's say I was to launch like a little voltage step right here. What's going to happen when it hits that point right there? What's it going to sort of try and do? Just from a very simple standpoint, like zero order.
Fill that via capacitance.
Say that again?
Fill the via capacitance.
Yeah, so basically the step is going to try and show up over here, and some part of the step is going to go that way. Some part of the step is going to go that way, right? Well, so then once that step shows up at the via cap, hey, you can't change voltages on capacitors instantaneously, right? So actually, initially, that wave is going to get completely reflected back. Well, now once it reflects back, and then of course it'll come back with the opposite phase, because it can say, hey, no, wait a minute, you can't actually put voltage here. And you can imagine now it's going to come back over there, and the negative step is also going to propagate over there. Of course, it's also going to go somewhat over there. As you can imagine, you can actually be creating almost something where if this negative wave comes back at just the right time, it could completely cancel the positive wave, right? In other words, this is a great way of creating a resonance, and that resonance usually takes away all of your signal, okay? It'd be really nice if you could create a resonance that gave you more signal, but life sucks, okay? So bottom line, it's not just that we're going to have actually sort of, that we're not going to be able to get signals from point A to point B because of things like dielectric loss and skin loss, but actually even just how we build this PCB up can actually cause some pretty nasty behaviors to happen. So the way we usually like to think about this is to really look at just basically what's the transfer function of that. You could say it's a transmission line, but really we call it a channel, okay? And by the way, people call these things channels because they just mean that's like the thing that's physically carrying stuff from the transmitter over to the receiver, okay? So whatever the set of wires and vias and etc. is in between those 2 points, that's usually what we call the channel. So if I take all those things into account, what I'm usually interested in is basically just how much attenuation am I getting from that channel versus different frequencies, okay? And remember, since we're trying to go at very, very high data rates, let's say 5 to 10 gigabits per second, something like that, then actually I'm going to care about the characteristics of that channel up to some pretty high frequencies. Okay? So I've just shown an example of a few different channels here. So basically of different lengths. So 9-inch FR4 is kind of like, that's a pretty, FR4 is the standard dielectric you use in PCBs. 9 inches, of course, is just the length of the trace. So you can see like 9 inches has a little bit less loss than, for example, a 26-inch. But then you can see that if I happen to have one of these vias in here, that's like creating these deep notches that I had talked about. That's those resonances that are taking away the signal. Okay? But basically what we can see is something like, okay, let's say I was going to operate where about 3 gigahertz is up to the frequency I care about. And we'll see how we come up with that in 1 second. You can see there's somewhere between about 20 to 30 dB of loss that this channel is introducing. So probably a lot more than like what we would have gotten from our on-chip wires, right? At least at most of the frequencies we were talking about. So really the question I'm going to ask now is, okay, fine, so maybe I know what the channel looks like, and maybe it's got a pretty large amount of loss in it, but how bad is that? In other words, how important is it that I have 20 to 30 dB of loss? So in order to answer that question, there's really 2 issues that we need to think about, okay? So the first issue is, okay, if I have loss, that means that if I put some, let's say, reasonably large signal at the transmitter, I'm going to get a smaller signal at the receiver, right? Well, if I get a smaller signal at the receiver, and that receiver is not perfect, it's got maybe a little bit of noise in it, which of course any receiver will, then the first thing I have to worry about is just, okay, can I actually correctly receive that signal with that small of an amplitude? Okay? So that's kind of the first thing that we're going to talk about, and we'll spend most of the rest of the day on that. There's actually another thing we have to worry about, though. If you look at this channel, it's not that I'm attenuating all frequencies exactly the same way. I'm actually attenuating the higher frequencies a lot more than I am the lower frequencies. In other words, this whole thing kind of looks like a low-pass filter. Well, so let's just think about what would happen if I took, at my transmitter, let's say this is like the pattern that I'm trying to send. So I have a 0, a 1, and then a whole bunch of zeros again. Okay? If I just pass this thing through some kind of low-pass filter, what's it going to look like at the receive side? Just in time, roughly, what is it going to look like? And by the way, let's say that this thing here is just 1 bit period. If I low-pass filter that, what's it going to show up on the other side? How's it going to look? Okay, it might be like an exponential, but maybe like even in more layman's terms. Yeah, it's flattened out or it's like smeared out, right? So I might get something that, let's say, looks like that, right? Where this is like my bit time, right? Okay, so why is this important? Well, notice this thing was supposed to be just exactly either a 1 or a 0, right? But when it shows up at my receiver over here, not only will I not necessarily get the same height as what I transmitted, but actually, for some amount of time later, for some number of the bits later, I'm actually still going to have some amount of voltage left over from that previous bit that I sent, right? That's bad news because if I was actually instead going to try and send another different bit over here, this leftover voltage is kind of going to screw me up, right? It might actually push me in the wrong direction. So we're going to spend a lot more time on this probably next time or maybe later today, but this is what's known as intersymbol interference. It just means that because of the frequency selectivity, or for example the low pass nature of the channel, or even actually band pass will do it too, basically bits run into each other and they create interference on each other. So we'll see that can also actually screw up whether or not we get the right answer at the end. So as I said, we'll spend a whole lot more time on that, but before we do, let's actually focus on this first issue right here, which is really, okay, if we've got noise, how do we decide whether or not we're really getting the right bit at the end? So to kind of answer that, we just need to do a couple of quick, let's say perhaps obvious, but point out a couple of things. So if I really have something where I'm transmitting just basically ones and zeros, so let's say that's my transmitter waveform. If I wanted to build a receiver that would basically tell me did I transmit a 1 or a 0, then essentially what you should really just be doing is, let's say that this is some plus delta V, that's some minus delta V right here. So let's say that that's 0, which of course we're going to implement probably in a differential way. Then if I want to receive that thing, basically all my receiver has to do is decide whether the input was greater than 0 or less than 0, right? Because if it was greater than 0, the transmitter should have been sending a 1. If it was less than 0, it should have been sending a 0. Okay, and I'm probably going to do this at a particular point in time, as we had talked about before. Okay, so in other words, what my receiver really should just look like, at least in the simplest case, is basically just a comparator, right? Where that comparator, in this case, has a so-called 0 threshold, or a 0 decision point, okay? So that's kind of like my ideal receiver, but unfortunately, no receiver is exactly ideal, okay? And there's really sort of two things that can be messed up about that receiver. So the first is perhaps the obvious one, which is any circuit that I build inside of this has some noise in it, right? It's going to have some thermal noise. Well, if you think about it, that thermal noise is kind of like saying that rather than exactly having 0 as my decision point, it's going to be jumping around that point, right? So there's going to be some like Gaussian distribution of what that actual decision point is, okay? So that's one issue, which we'll spend most of the time on. The other is, of course, that I have to do this at a particular point in time. If I don't do it at exactly the right time, let's say I sample it over there or over there, then I might actually get a slightly different answer. In fact, I might even get the wrong answer. Okay? So in order to kind of understand a little bit like how bad or how good this receiver has to be, the way we usually like to sort of take a look at that is to look at what's called the eye diagram. Okay? So all this eye diagram, which is shown right here, is doing is it's basically just, let's say if I look at the transmitted bits, so let's say I had something that looked like, I don't know, like this, where each one of these is a bit time. All that eye diagram is doing is it's just going to take each of those transmitted bits, like the time axis for each one of those transmitted bits, and just overlay it all onto the same spot, okay? So it's kind of like, rather than continuing my time axis always from left to right, every bit period, I reset it and I just draw the same thing on top of each other, okay? So the reason this is useful is, imagine I had a perfect transmitter, okay? Then if I looked at that eye diagram, it would basically look something like this, okay? So there'd just be sort of like this perfect square box there. What this basically tells you is, okay, I'm always either going to get a perfect plus delta V or perfect minus delta V, and it's always going to transition exactly at these times. In other words, as long as my receiver samples anywhere within this time window, it should get the right answer, right? And as long as its noise is smaller than what's inside of this box, it should also get the right answer, right? In other words, the more sort of white space there is in the center here, the more basically garbage I can tolerate in the receiver, okay? Now, of course, this doesn't look so much like an eye, but any real transmitter actually has a finite edge rate. And of course, the levels up over here won't be perfect. They'll have some fuzz band around them. And so you can actually kind of already see this based on my, highlighter marking here, but real eye diagrams look something like this, okay? And that's really why they call them eye diagrams, because the smeared out edges on the two sides kind of make it squint a little bit, okay? So now, basically we know that there's going to be sort of these two issues, right? So there's noise in the voltage domain on the receiver, and there's also going to be some timing noise. So for now, let's again just assume that we can do the timing perfectly. So what I'm going to be interested in is essentially what's going to be the impact of the voltage noise of the receiver. Well, the way I can kind of characterize that, or the way that I'm going to sort of decide whether or not I can tolerate that voltage noise, is that noise, of course, has some distribution associated with it, right? So because this is a Gaussian distribution, it's always possible, even though it's very unlikely, that the noise will eventually be large enough that I actually get the wrong answer, okay? That actually this noise is like larger than my signal. Well, so in the standpoint of links, what you really then care about is basically how often is the noise going to be big enough that you get the wrong answer, okay? In other words, what you usually care about is something called the bit error rate, or BER. And that's really just essentially what's the average number of bits that you received incorrectly over the total number of bits that were transmitted and received in your system. So now, just to see if you guys are maybe sort of paying attention, for some of the stuff that we're talking about, what do you think is sort of a good or acceptable bit error rate? Let's say inside of like your PlayStation 3. What do you think is the kind of bit error rate people would be interested in?
10 power minus 5.
Okay, you said 10 to the minus 12. Somebody else said, what, 10 to the minus 5? Okay, so I think you're closer to correct, but let's see, where would that number come from? Why would you care about, like, let's say 10 to the minus 5 versus 10 to the minus 12? What would that kind of mean in this context? What happens when you get a bit wrong? What do you guys think?
Your digital word is corrupted.
Okay, the digital word is corrupted. So let's say, just as an example, this was my laptop and it was, I don't know, my processor talking to my, let's say, the memory, and I got some completely wrong bit in there. So that I go and I talk, instead of talking in one memory location, I talk to some like completely different memory location. What usually happens when you have something like that?
Boom.
Yeah, boom, right? Blue screen of death, right? Something goes really horribly wrong. So in other words, now obviously usually you have some kind of error correction in there, but bottom line, what sets basically how much you care about this bit error rate is how often can you tolerate making errors. Well, I don't know about you guys, but at least for me, if it's my laptop, I want to make sure that it basically never makes errors, right? Probably over the lifetime of how long I'm going to run the thing. So now, if I'm running at, let's say, 5 gigabits per second, and I had a bit error rate of 10 to the minus 5, on average, how often would I be making mistakes? You guys are laughing, so you got the right idea. So how often would I be making mistakes? And I don't need a number, but
In times a second or something?
yeah, all the freaking time, right? Okay, so 10 to the minus 12, I like that number a little bit better, because then I guess I at least get, actually, I get about 200 seconds or so. But my lecture is about 80 minutes, so I at least need that long, right? So I probably need another few orders of magnitude on top of this, right? And by the way, 5 gigabits per second is just like one of the links. I probably have about 1,000 of them, right? So typical numbers you need in these kinds of systems are around 10 to the minus 15 to all the way down to around 10 to the minus 20, okay? So like in memories, because they really, really don't ever want to make mistakes, it's about 10 to the minus 20. In something like, maybe Ethernet or some of the other IOs, Ethernet actually, the raw links run at maybe about 10 to the minus 5 or 6, but there's some big error correction code on top of there. But like in some of the chip-to-chip IOs, you're probably talking about 10 to the minus 15. Okay? So, now that we know sort of, okay, there's going to be a certain bit error rate that I'm going to want to hit. So I'm going to want to make sure that my link doesn't make mistakes at a certain rate. And what I can basically do is now figure out what's really going to be the minimum signal amplitude that I need to support in my link. Okay? And the way to do that is actually fairly simple. So essentially we just kind of have to keep sort of two things in mind. So remember we said that when we build our receiver, that's essentially just going to be a comparator. That's just going to decide if the input is bigger or smaller than 0. Well, unfortunately, you can never really build a perfect comparator, right? So that comparator is always going to have sort of two things. First of all, it's always going to have some residual offset. In other words, even though you wanted it to exactly compare at 0, maybe instead it's actually got like 5 millivolts of offset or 10 millivolts of offset. So if we kind of think about that on our eye diagram, what that means is that even though we wanted the decision point to be right there, maybe it's actually shifted up a little bit. Maybe it's actually, let me do that in a different color so it's easier to see. Maybe it's actually like over there somewhere, okay? Where there's some offset here. Okay, well, so obviously my input signal had better be larger than that offset, right? That's pretty clear. But I'm not only going to have that offset, I'm actually also going to have some thermal noise, right? So what I'm going to do now is I'm going to draw this in a little bit funny of a way, but I'm just going to draw a picture, and it's actually, I think, already on your slide, of basically how big will that thermal noise be versus what's the probability of actually getting that amount of noise. Okay, so it's going to look something like that shape right there. Let's say it's a Gaussian. Okay, so like something that's larger, you know, in the left direction means it's more probability. So obviously the mean should be 0, but I have some probability of getting things larger than that, obviously. Okay? So if I want to know how often I'm making a mistake, what I basically need to do is just look at, okay, from this offset point, how probable is it that my noise will be larger than my signal, right? Because if it's larger than the signal, then essentially the receiver is going to see, in this particular case that I just shaded, rather than seeing something that's a 1, it'll interpret that as a 0, right? So in other words, what I'm really interested in is exactly this shaded area under here. Because that shaded area, that's like the total probability of getting noise that's larger than the difference between my offset and my input signal right there. Okay? So what this basically says is that if we want to know like what's the minimum input signal we need to give to this comparator, it's just set by this area under the curve right there, which, you know, in case you haven't seen statistics in a while, this is set by the so-called complementary error function. Okay? So this area, in other words, once I know that area under the curve, if I want to know the bit error rate, it's just set by 1/2 times ERFC of the input signal amplitude, which is really just, that's the amplitude right there. Of course, minus the offset, because that's the distance from my decision point. And then divided by this square root of 2 times sigma noise. Okay? So turns out this ERFC is a horribly complicated, disgusting function. So it's not that I'm going to be making you do a whole lot of stuff with it. By the way, this whole thing here is also known as like the Q function. But the good news is there's actually a really easy way to interpret this whole thing. Okay? What it basically tells you is the following. If there's a certain bit error rate that I want to achieve, then I just have to make sure that V in minus V offset is larger than a certain number of sigma of my noise. Okay? So as an example, if I want 10 to the minus 12, V in minus V offset better be larger than 7 sigma. If I want it to be 10 to the minus 20, better be larger than 9.25 sigma. Okay? So what you can always do is if somebody tells you what's the bit error rate you want, you just go, you calculate this function, and you figure out, okay, how many sigma do I need in order to hit that particular bit error rate? Okay? You can kind of do that just as almost a lookup table. Yeah? That's right. Sigma is the standard deviation of the noise, right? So like, you know, if we sample onto a capacitor, the sigma squared is KT over C. Okay? So that's basically how we use this. Now, just in case you haven't sort of noticed this already, what's inside of here, this V in minus V offset divided by square root of 2 times the sigma of the noise, that's very similar, or it's really almost exactly the same as just SNR. Okay, because it tells you something, actually really it's the square root of the SNR here. But it's just saying, okay, what's the signal amplitude versus the amplitude of the noise? Okay, so much like we've already talked about, essentially the SNR is going to set how often we're making mistakes. Okay? Does this kind of make sense to everybody? Or? Okay, so the question you might naturally ask now is, so what? Right? So, okay, fine, we figured out what the minimum signal amplitude is. Maybe that comes out to be 10 millivolts or 20 millivolts or even 50 millivolts. So, okay, fine, we know what that is. Why don't we just basically build a transmitter that has way, way bigger swing than that? So why don't we make it like 400 or 500 millivolts or something? So you might at first think, well, this is sort of a stupid question, but in fact, turns out oftentimes that's exactly what people do. Okay, but hopefully I'll try and convince you that maybe that's not actually the best way of doing things, particularly if we care about low power consumption. So it's actually, if you really want to know, it's a much more detailed sort of discussion, but here's a couple of sort of simple hand-wavy answers. So the first thing is that the impedance of our transmission lines is usually pretty low. If you guys remember, I said it's usually about 50 ohms. Remember, low impedance means that if you want big voltage swings, you need a lot of current. Okay? So as an example, if I wanted to do a 1 volt swing on 50 ohms, that's going to take me about 20 milliwatts. Okay? And I'm going to claim that oftentimes that's just too much. Okay? Because in fact, if you think about it, on the receiver, if I wanted to generate that same 1 volt of swing, actually I claim I can do that probably with a lot lower power. And maybe in fact I don't even need that much swing. But even if I wanted it, I can probably do it with much lower power. Why do I say that actually on the receiver I think I can generate larger swings with lower power? Why do I say that? Any thoughts?
You're now using on-chip wire.
Ah, okay, that's basically it, right? On the receiver side, just as an example, okay, so we said we wanted to terminate our transmission line, right? But let's say I just stick a little amplifier in here, and I have that amplifier drive my comparator. So what's going to set sort of how much power it takes that amplifier to generate a certain amount of voltage? Or let's say even to get a certain amount of gain bandwidth.
It'd be a lot better because you're not having to drive 50 ohms. You can drive a lot bigger.
Exactly. This comparator here probably just has a capacitor at the input, right? Remember, at DC, the impedance of the capacitor is infinite. So to get sort of the same voltage swing, since this impedance is probably a lot higher, costs me a lot less power. Okay? So in fact, I'm going to kind of argue that a lot of times, rather than just putting a really big swing over at the transmitter, instead, maybe you're just better off putting a little bit of gain at the receiver. That gain is just a heck of a lot cheaper because the impedance you're driving is a lot higher. Okay? So that's kind of the first reason. The other reason is, and we'll see this more next time, is that actually, if you remember I said that because we have this frequency selective stuff, the bits get smeared out. Well, the amount of bit I have left over is proportional to how much I transmitted in the first place. Okay? So no matter how big I make the swing, the relative impact of that is basically constant. So if I have something that wasn't going to work because of bits being smeared out, doing bigger swing ain't going to solve the problem. Okay? So the bottom line here is that essentially, if you can build things that have lower transmit swing, because this impedance is so low, in general, you can actually get lower power. Okay? So that's, of course, good news, because it means that if we can figure out how to build very low power but very low noise receivers, meaning amplifiers, we're in good shape, right? So we've got lots of stuff to do with our 240 material. Okay? So what I just want to sort of really quickly do with the last 10 minutes here is just kind of give you an overview of what a few of the circuits kind of look like. And in particular, this is kind of going to get you going on the project. Okay? So just really quickly, just so that you sort of have an idea, you're not probably going to be building much on the transmit side, but just so you have an idea of what they typically look like. Since you're going to build these links in sort of oftentimes these big systems that have lots and lots of junk on them, you're going to worry a lot about noise. Okay? And so if you worry about noise, again, oftentimes, and by the way, by noise I mean just sort of man-made noise of, let's say, digital gate switching and stuff like that. We're going to try and make all that essentially common mode. In other words, we're going to try and use differential circuits most of the time. So it turns out one of the most common, basically, transmitters you're going to see is actually a really, really simple circuit that we've, of course, drawn about a bazillion different times already. It really just looks like a differential pair driving a resistive load, okay, and then driving, of course, the transmission lines. Okay? The only real sort of trick I'm going to play here is, because I want to make sure that my output impedance matches the transmission line, basically I'm going to make this 50 ohms right here. Okay, and so just to be clear, I'm going to drive this, of course, with the digital data, and just with digital data on one side and the complement of the digital data on the other side. Okay? So this is kind of like this so-called, they call this, by the way, a current mode transmitter, because this circuit down at the bottom, the actual active circuit, is basically just a differential pair that's steering the current one way or the other. Okay? There's other ways of building these types of transmitters, but basically if you do something where it's set by sort of currents, that's called a current mode. If you do something where you're literally just switching voltages back and forth, they call that voltage mode. Okay? But just really quickly, the good news about this design here is that it's really simple and it's pretty robust. Okay? There is one piece of sort of bad news though. Okay? The bad news is that basically the power is not really as good as it could be. Okay? And the reason I say that is the following. If you think about it, if I'm really just steering currents back and forth, this thing down on the bottom, I always need some minimum voltage across it, right? Some, let's say, K times V star or something like that. Right? And if I want those switches to act like, if I want this whole thing to act like a good current source, I probably want another K times V star across those switches too. Okay? In other words, that means that I have to make this voltage up over here large enough that I can get the swing I want, plus still keep these switches in saturation. Okay? If you compare that to some other type of topology where I just directly switch the voltages onto the line or back, that basically means I'm burning some extra power because I needed higher voltage to keep these things saturated. Okay? So in the sort of most of the project, I will give you a transmitter that looks like this, but just be aware that's not necessarily the most power efficient transmitter you could build. Nonetheless, still people typically use this just because it's really simple, it's really robust. Okay? Okay, so now we kind of know what the transmitter is going to look like. So the next thing is sort of, well, what are we going to do at the receiver? And in particular, how are we going to terminate that receiver? So I'm just going to quickly draw sort of the standard way that this is done, because I want to get to sort of a couple of other things first, and then maybe next time we'll come back and sort of finish up all of the other options. So let's assume that we use our current mode transmitter, which, just as a reminder, basically that's just a diff pair. And I have my two 50 ohm loads right here. And then I have my receiver right there. So the most common way that people will hook this up, so remember I need to terminate the receiver also. So the most common way that people hook this up is just also to take two 50 ohm resistors and connect them right at the inputs right there. Okay? So now, this is obviously really easy to do from a termination standpoint, but this has some obviously implications on the design of the receiver. So in particular, if I build this thing this way, what's going to set the common mode at the input of my receiver? What's that going to be set by? Okay, it's going to be set by the transmitter. What is that output common mode of the transmitter? Which, again, maybe I'll just draw the half circuit for the transmitter with the receiver. So I've got some IB, I've got some 50 ohms right here, got another 50 ohms right there, and this is some VDD. So what is that common mode going to be set by?
Not really anything.
No, it is set by something. I mean, I've got IB that's going to be flowing through 50 ohms. And of course, it's going to flow through a transmission line and flow through another 50 ohms over here. So what's like the equivalent resistance looking up into that? 25 ohms, right? At least at DC. So what's going to set the common mode at the receiver? What's that going to be? I have 25 ohms of resistance, and how much current's flowing through it? On average.
Half IB.
Yeah, half of IB, right? So remember, the swing is really just IB times 25 ohms. So in other words, the common mode is just going to be VDD minus V swing over 2. Okay? In other words, the common mode is going to be directly tied to what's the swing that you're using. Okay, so the larger the swing, the lower the common mode. If the swing is very low, you have a very high common mode. So if you pay attention in the project, you'll see that I actually gave you the opportunity to use a different common mode if you want to. So it's actually a little bit nice to you, so to speak. But in the later phases of the project, you'll actually have to really build it. So you'll have to figure out sort of how to really make it work with the right common mode. But as we'll see, there are a couple of other options you can use to actually tweak the common mode slightly. But basically, common mode is really tied to what you're doing on the transmitter. So just keep that in mind when you're doing your design, because it's something that's definitely going to pop up again later. So we'll come back to some of the other options in a second. But what I really wanted to do is just sort of see, okay, what's like the most basic receiver that I might actually build? And as I kind of motivated a little bit already, my argument's going to be that if we want to build sort of the most basic receiver, it's probably going to look something like this. Okay, so there's probably going to be some sort of front-end amplifier driving a comparator, where in particular, it's likely that that front-end amplifier could even be something as simple as just a resistively loaded diff pair. Okay? So as we already talked about, the reason I say that I probably want this front-end amplifier is that basically I want to make sure I get enough voltage swing at the input of the comparator, but I don't want to pay a lot of power for it. Okay? So as we'll see a little bit later, you could kind of argue, well, okay, what's the difference between what's inside of this comparator and what's this amplifier? Well, we'll see a little bit later when you build comparators, they tend to have a lot of devices. Okay? Having a lot of devices tends to mean if you have a lot of devices, that tends to mean you have a lot of noise, and we'll also see later, you also tend to have a lot of offset. Okay? So even though the circuits inside of that comparator look sort of somewhat similar to what's in this front-end amplifier, I'm going to claim oftentimes you want to do something like this, just to overcome the noise and the offset of the comparator, just to make sure you get enough signal swing that the whole thing works correctly. Okay? So just really quickly, there's just sort of a last couple of things that I want to just briefly mention here. Okay? So let's assume that indeed this is how we build our receiver. Okay, so we have some front-end amplifier and then a comparator. If you notice in your project, I didn't tell you anything about what the gain of that preamp should be. In fact, I claim it's totally up to you to decide what that gain is. So, if you come and you ask me, what is the gain? I'll say, I don't know, I don't care. It's up to you to figure out. Okay? But that's not to say that obviously it's a totally free variable. So if you look in the project, I told you what the input amplitude is. Okay? So I just assumed that I knew what the transmitter was, and I told you that input amplitude. And I actually also told you what's the offset of the comparator? Okay? So if I told you those two things, and let's say, and actually I did also tell you, I believe I specified that I wanted a burr of, I don't remember, but I think it was 10 to the minus 12. So if I told you all that stuff, how would you go about deciding what gain you should use in a receiver? What sort of equation should you be using? Yeah.
The Burr equation?
Yeah, exactly. It's going to be the bit error rate equation, right? So just as a reminder, what that bit error rate equation says is if you want, let's say, 10 to the minus 12 burr, then I have to make sure that the signal going into the comparator minus the offset is larger than some number of sigma times the noise. So what is the signal going into the comparator? What's that going to be set by? Let's say this has a gain of A. Yeah, so the signal going to the comparator is just A times V in amplitude. I have to knock off the offset. And then I just want to make sure that that's larger than, I don't remember what the number is for 10 to the minus 12. I think it's 7, but I'll just call it K. That has to be greater than K times the noise. Okay? Okay, so this is actually exactly the equation you're going to use, but is there one minor sort of trick or detail you have to be careful about here? What do you guys think?
Need to add the noise figure of the amplifier.
Ah, okay. Basically, this noise inside of here actually depends on the design of the amplifier, right? So in particular, let's say I had a resistively loaded amplifier. What is the noise of the output of that amplifier going to be? Integrated noise.
KT over C times 1 plus AV.
Gamma AV, there you go. Right? So in other words, this equation here is just a little bit more fun because the noise actually depends on your gain also. Okay? But basically that's exactly what you're going to have to use to figure out how much gain should you actually be putting into this thing. So just one last thing, we'll go a little bit long today, but just to kind of get you guys all set up for the project. The one last thing that, again, most likely somebody who's looked at the project will come and ask me is, okay, fine, maybe now I know how to do the gain, but you didn't tell me anything about how much bandwidth you need. And again, that's absolutely correct. I did not say anything about how much bandwidth. Because the reason is, you should be able to figure that out. Okay? So the thing to keep in mind is, again, if I have this front-end amplifier sitting in front of that comparator there, that bandwidth, if that amplifier has only a finite bandwidth, that basically means that if I look at the bits that I sent from the transmitter, as I change the bandwidth of that receiver, what's basically going to happen is I'm going to basically respond to like those bits with some different amount of settling time, right? So if this is like a high bandwidth, as I reduce the bandwidth, I'm going to get like this exponential settling, right? So I'm going to get waveforms that kind of look like that. Well, what's bad about this one with a low bandwidth? Why is it that I might be unhappy about the fact that this thing looks this way? Even ignoring all this extra junk that's after here. Okay, it's got higher bit error rate, but why? Yeah. Comparator may not be sensitive. So let's assume that I have a perfect comparator that's always going to sample at exactly the time where I have the peak voltage that I get. What's worse about this particular, that particular thing right there versus the higher bandwidth one? I think I heard somebody say it. Just speak up.
SNR.
Yeah, the SNR is worse, right? I have a smaller input signal, right? In other words, because I didn't settle all the way, I'm getting a smaller voltage difference that's fed into my comparator, right? So basically what I'm saying here is that in order for you to decide what bandwidth you should be using, it's really going to be set by how much loss of signal